Alright, welcome to lecture 19. In this lecture we'll derive the solution to the general cubic equation. So let's begin by reviewing the solution for the n equals 1 and n equals 2 polynomial equations. Alright, so n equals 1 we've been doing for a while. So that's just a linear equation. If you have ax plus b equals to 0, you want to find the solution. Well, solve for x, right? Just isolate x, and that worked pretty well, didn't it? Minus b over a. And you can do that as long as a is not equal to 0, right? Okay. N equals 2, well, that's where we do completing the square, right? So we start with ax squared plus bx plus c for a non-zero, factor out the a, right? And then complete the square. So we group all of the x terms together by putting them in a square, and that way we isolate x as a square equal to this quantity over here. And then we take the square root of both sides, and that gives us x plus b over 2a equals to plus or minus the square root of all this stuff, right? Now, as I discussed in our complex lecture, this still makes sense when a, b, and c are complex. It's just then you have to take the square root in the complex sense, right? Now, the technique of completing the square has sort of an analog for cubics, and I'll follow the presentation of Rotman in his text on Galois theory, second edition, pages 44 and so forth. So Rotman is a prolific author. He wrote many books on mathematics, and a lot of people write a lot of good math books, but if you study Rotman's books, you'll notice that his presentation it exceeds many others. It's anyway, I have a lot of praise for Rotman. That's why you find me using Rotman here and there in different courses. But anyway, moving on here. So how do we do the cubic? All right. Well, first of all, we need to take a step back here and get a general idea, which is to talk about a polynomial being depressed. All right. Although I think Rotman uses the term reduced, but I've seen the word depressed used more generally. So a polynomial of degree n is depressed if it has no x to the n minus 1 term. So it skips over the next to leading order term. So it goes from n to n minus 2 when you look at the polynomial, all right? And it turns out that if we have a monic, that means leading coefficient is 1 polynomial, right? Then we can turn it into a depressed polynomial by making the substitution of big X equal to little x minus 1 over n, a sub n minus 1. So like in the quadratic case, that's the completing the square trick, x minus 1/2 b. Make that substitution. Well, we'll see that down here at the bottom of the page. But anyway, here's the lemma. If we replace big X with little x minus 1 over n times a to the n minus 1, that gets us a depressed polynomial. Let's call it f tilde of little x equal to that. And moreover, if u is a root of the depressed polynomial, then u minus 1 over n times a to the n minus 1 is a root of the original polynomial. So the proof is just a straightforward calculation. Let me scooch this up a bit here so you can see it. Proof is just a straight calculation here, and it's like let big X equal to little x minus 1 over n minus 1. Plug it in here, plug it in here, plug it in there. Expand those out, binomial theorem, right? The next to leading term is n times x to the n minus 1 times minus 1 over n a sub n minus 1, right? And then the leading term in the second term is a to the n minus 1 times x to the n minus 1. So this guy, right, this guy here, and this guy here, they cancel, right? These guys cancel. And that means that we have no next to leading order term in the substituted polynomial, which we define to be f tilde of x. Now, here the constants b sub n minus 2 to b1 and b0, these are somewhat complicated and involve the original coefficients jumbled around a bit. And we'll see how these coefficients are given for specific case, just the specific case of n equals 2 and n equals 3 in this video. And then finally, if f tilde of u is equal to 0, then f tilde of x equals to that. So that means that f of x is equal to replacing x with f tilde with x plus 1 over n a to the n minus 1. So anyway, you just sort through it, and you can see that f tilde of u is equal to 0 as desired. All right. Now, well, this is given. What's surprising, or not as surprising, but what's interesting is that the original polynomial at u minus 1 over n a minus 1 is 0. So here's the application of this general lemma to the n equals 2 case, all right? Which of course we've already solved with completing the square, right? But this is a slightly different, kind of a tricky technique that replaces. It's like completing the square except using a substitution is how I would describe it. But so f big X, x squared plus bx plus c. This is the arbitrary monic quadratic, and then I substitute x minus 1/2 b in for big X and square that thing. This defines f tilde, right? And when you square these things out, the bx terms cancel, and you're just left with x squared. This c is that c plus c, and then if you look at it, you get a plus 1/4 b squared from this, and you get a minus 1/2 b squared from that. So that gives you a net of minus 1/4 b squared. All right. So f tilde of x equal to 0. That's easy to solve because that just gives you u is. If u is the solution, that gives you u equal to plus or minus 1/2 square root of b squared minus 4c. Oftentimes we wouldn't write u there, we'd just write little x, okay? But anyway, those are the solutions to the depressed quadratic. And then using the lemma, the solutions to the original quadratic are the depressed solutions minus a sub n minus 1 over 2 in this case, which is minus b over 2. And of course we recognize that as the quadratic formula, in the case a equals to 1. All right, so let's take this out for a spin in the cubic case. So I'll start by just looking at the arbitrary cubic with leading coefficient 1. If the cubic doesn't have leading coefficient 1, if the cubic for some reason wasn't monic, we could always divide by the leading coefficient and make it monic. So leading coefficient 1, I make the substitution x minus 1/3 a, following the lemma, and I do the algebra. That gives me a depressed polynomial with coefficients b minus 1/3 a squared, 2/27 a cubed minus 1/3 ab plus c. So if I set q equal to b minus 1/3 a squared and r equal to 2/27 a cubed minus 1/3 ab plus c, this gives me g tilde of x is x cubed plus qx plus r. So let's just remember that if we can always take a cubic which is not depressed, and we can make this substitution and turn it into a depressed cubic. And we also know from the lemma that if what's the rule? If g tilde of u equals 0, that implies what? That g of oh goodness gracious, I've already forgotten it. Then if u is root of f tilde of x, then u minus 1 over n a to the n minus 1, then u minus 1/3 a is equal to 0, right? So in other words, if we can solve the purple one equal to 0, right, that will then naturally give us back the solution to the original, big G of x equal to 0. All right, so let's get to it. How do we solve this blue one, the purple one rather? All right. So consider g tilde of x equal to x cubed plus qx plus r, right? And we're going to follow some substitutions that go back to some, see if I've got the, one moment here. So this is the relevant pages from Rotman. He says this coming formula was essentially due to Scipio del Ferro about 1515. A similar formula was discovered by Tartaglia about the same time, and both appeared in print for the first time in the book of I think that's Cardano in 1545. The interesting of the history of all three of those people is, and their interrelation is interesting, and there's a great YouTube video made about it, which I think I've sent at least one of you. But anyway, so at least in Europe, solution of the cubic has been known since about 1500, and the solution to the quartic, the fourth order problem, came not too long after that. So anyway, let's focus on the cubic here. I'll say a little bit more about solving polynomial equations in general at the end of this lecture. But oh, lest I forget, the secret word is Voltron. All right, Voltron. So suppose you had, here's the way that we go. We're going to suppose you had a solution u, which you could write as the sum of y and z. All right. Then what we're going to do is we're going to derive conditions on y and z. All right. So this alone is not enough to explain what the y and the z mean. We need another condition actually. We'll get to it here in a second. So if u equals y plus z is a solution, if you cube y plus z, you get this, all right, which you can rewrite in terms of y cubed plus z cubed plus 3uyz, all right? And then we need that to solve the g tilde of x equal to 0 equation, so that would give us u cubed plus qu plus r equal to 0, which gives us this by this equation up here, this expression up here, right? The u cubed becomes the y cubed plus z cubed plus 3uyz, plus the qu plus r, right? And then the next step, we factor the u out. That gives us 3yz plus q times u plus r equal to 0. Well, this equation 1 is pretty nice, but what would make it ever so much nicer is if we could just also impose that 3yz plus q is equal to 0, all right? So this is the kind of thing we do in differential equations a lot, right? When you're finding a solution, you make a guess of what the solution looks like, and then if that guess is still kind of like a little bit too slippery, we add another condition to the guess. And sometimes if you add enough conditions to the guess, then it kind of fixes the guess to be a specific thing, at which point then you can go back to the original problem, plug it in, and see if it actually works. Now, when you're making a guess and you're adding conditions, you can always add too many conditions, right? But it turns out that this is not too much of a burden. Like adding this condition does not ruin the solution. So let's see how that goes. Now, so Rotman has a homework problem about why this is reasonable. All right, maybe I'll assign that. We'll see. Y cubed plus z cubed plus this plus that equal to 0. So if we make 3yz plus q equal to 0, then equation 1 just becomes y cubed plus z cubed equals to minus r. And if we have 3yz plus q equal to 0, that's the same as saying yz is equal to minus q over 3, all right? Which then, if I want to turn that into like a cubic equation, I cube this, and that gives me y cubed z cubed equals to minus q cubed over 27. Well, this is nice because I've just got everything in terms of basically y cubed, z cubed, and let me scooch this up a bit here. So then we take the y cubed and we solve that for z cubed. Z cubed is minus q cubed over 27 y cubed. Plug that in for z cubed here. That gives us this. Then, if you multiply this by y, multiply that by y cubed, it gives you y to the 6 plus ry cubed minus q cubed over 27 equal to 0, which then gives us a quadratic in y cubed, which we can solve by the quadratic formula to give us this, 1/2 minus r plus the square root of r squared plus 4q squared over 27. Q squared? I don't know if I believe that. I think that's a cube. That is a cube. Fortunately, I haven't scanned this yet. So that's just the quadratic formula applied to this equation here in the variable y cubed. Okay, so like you can rewrite this as like, let's say lambda squared plus r lambda minus q cubed over 27 equal to 0. So lambda is equal to, 1/2 minus r plus or minus the square root of r squared plus, minus 4ac in this case is plus 4 q cubed over 27. Now the plus or minus doesn't really concern us. We just want one solution, so we'll just take the plus. And great. So equation 2 gives us a solution for y cubed, which then, once we know that, we can go back and we can figure out z cubed from up here, right? And, well, I mean, z is, once you know y, this gives you y cubed, right? Then you can take the cube root of all that, right? And that gives you y. And then you put z minus q over 3y, add those together, that solves the problem. Now, in order to properly understand all this, notice that we're going to possibly have to take both the square root and ultimately the cube root of a complex number, actually. So this is one of the places in mathematics, and we'll see this as we go on here, that we're solving a real problem, possibly, right? Q and R could be real. I think of them as real to start with, okay? And even though Q and R are real, you've got a cube here, so that could be negative, and this could, of course, work out to then be an imaginary number. This could be a complex number. You have to take the cube root of a complex number, yeah? So to really understand how to solve this substitution, even for a real problem, it necessitates the use of complex variables. Before, when we ran up against complex numbers for the quadratic, we could comfort ourselves in saying, oh, yeah, but the complex solutions don't correspond to physical problems, right? Like, if you think of it graphically, those are the ones without x-intercepts, right? Or the ones for which that, the picture about completing the square maybe doesn't quite make sense. But for this, even for cubics which are real, with real answers, we'll see we get complex numbers in the midst. All right, so continuing here, I should probably keep that other page I just went past handy. Probably need that again. Remember, omega is I'm using omega for the third root of unity in this lecture, if that's okay with you guys. Well, even if it's not, I'm going to. So 2 pi I over 3, which, by the way, is minus 1 plus I root 3 over 2, because cosine of 2 pi over 3 is minus 1/2, and sine of 2 pi over 3 is root 3 over 2. And if you square that, you end up with minus 1 minus I root 3 over 2. It turns out omega's complex conjugate is omega squared, right? If you think back to the lecture where we talked about roots of unity, you could picture, I'll draw it in here. Actually, wait a second here. Like so. Oh, my other thing's gone. But anyway, so 1 is here. Basically, this is omega. And this is omega squared. All right, so they're symmetrically situated about the origin. Anyway, so if we have y naught cubed is 1/2 minus r plus the square root of r squared plus 4q squared, not squared. Oh, snap. How many times did I do that? I've got it cubed later on this page. Watch out for that. Anyway, so we got y naught squared, it gives us this, right? If that's the case, then if you multiply y naught by omega, or if you multiply y naught by omega squared, what happens? Right, you got y naught omega cubed is what? Equals y naught cubed. Omega cubed. Omega cubed is 1. So that's the same as y naught cubed, right? And likewise, if you take y naught omega squared, and you cube it. You get y naught cubed omega cubed squared, right? Which is again 1, so you get y naught cubed again. So if we have one solution of the cubic, y naught cubed equal to 1/2, but rather 1/2 times minus r plus the square root of r squared plus 4 cubed over 27. Man, we need to give that a name. Then then we have two other solutions because we can multiply by the third root of unity and the square of the third root of unity, all right? So in summary, we'll have g tilde of u equal to 0 for u equals to y plus z, where z is equal to minus q over y over 3y, provided that we make y, well, we have three different solutions. One is with y naught, which again I'm saying is the solution to this equation right here, right? And then we get y naught plus z, where the z is equal to that. And then we can replace y with y naught plus omega, y naught times omega. So then z gets a division by omega, but by the way, division by omega is the same as multiplication by omega squared. Fun fact. Man, there's all kinds of neat things about the third root of unity. Here's another one. 1 over omega equals to omega squared. So that's a fun fact about the third root of unity there. And so that's why this is equal to that. Why is that plus? Should that be minus? What was z? Oh, the minus goes into the z. Z naught is minus q over 3 y naught. Okay, great. So plus z naught omega squared, and then y naught omega squared plus z naught omega. All right? So these are my three solutions to the cubic equation. Oh, I already told you over here. I just wrote it again up here, my bad. And so just to, again, to kind of summarize things thus far, here's a recap. Here's the cubic formula. To solve the depressed cubic equal to 0, it suffices to set u equal to y plus z, where u is equal to y plus z, or u is equal to omega y plus omega squared z, or u is equal to omega squared y plus omega z, and y solves y cubed equal to 1/2 minus r plus the square root of r, and z is equal to minus q over 3y, where we've finally given a name for the thing under the square root. We've defined it to be big R, which is r squared plus 4q cubed over 27. Let me see, I think there's a name for that thing. Does he say? I want to say it's, well, I better not say that if I don't know for sure, but that probably has a name. Oh well, I'm sorry guys, I don't remember the name right offhand. But anyway, we'll call it big R for the purpose of this lecture. That'll do fine for us. Certainly big R could be negative, which means the square root of R could be an imaginary number, right? Okay, now, but no problem for us though. We know how to solve the square root of a complex number, and we know how to calculate the cube root of a complex number, right? We just put it in the polar form like we did before. All right, so let's look at an example, an explicit example. Here it is, example 2. Where's my cover sheet gone to? One moment, here it is. So we have x cubed minus 15x minus 126 equal to 0. It's already depressed, thankfully, and the coefficients q is minus 15 and r is minus 126. So we calculate the big R, which is r squared plus 4q cubed over 27. We get 15,376, which is obviously 124 squared. Ha ha ha. The square root of r is 124 then. And so what we're facing with our y cubed equation, y cubed is 1/2 minus r plus root r, which gives us 1/2 of 126 plus 124, which is 250 divided by 2 gives me 125. What's the cube root of 125? Oh, it's 5. Hooray! And this example is just so cheesy. I mean, this is such reverse engineering of a cubic to make the equations here as nice as possible. Z minus y, this is in Rotman. This is what I mean in part by Rotman's writing being so beautiful at times. He does these sorts of things. Z is equal to minus q over 3y, And so that in this case that's 15, minus 15 is 15, and y was, we figured out was 5. So the z works out to 1, z is equal to 1, hence y plus z is 6. U equals to 6 is a root of that, all right? And the other roots are 5 omega plus omega squared and 5 omega squared plus omega. Those are the other roots. Now we can be explicit. Omega is this, omega squared is that. When you add them, you get minus 3 plus 2i, minus 2i root 3. And the other one, when you do 5 omega squared plus omega, let me move this up a bit here. When we do the other one, 5 omega squared plus omega, this gives us, this is the omega squared, this is the omega. We add them, the minus 1/2 terms give us minus 6 over 2, which is minus 3. And here we get like minus 5 plus 1, which is 4. Wait a minute, that's be minus 4. I wonder if I've got these backwards. This gives me 5i minus I, which would give me, oh, I'm sorry guys, I got the plus and the minus switcherooed. Let me fix that. This is plus and that one's minus. Because we get minus 5i over 2 plus I over 2, which gives me a minus 2. Sorry about that. Don't want it to be confusing. Oh, come on. Well, I tried. Give it a second. Well, and now, okay, so you can use these multiplication by omega and omega squared to get the second and the third root. The other thing you could do, once you have one root of a cubic, and there always is one root, isn't there? You can divide by it, right? You can divide by x minus it, and that'll give you a quadratic, which then we can solve by the quadratic equation, right? So pragmatically speaking, that may be an easier way to solve, like to factor the cubic, like divide out the linear term here, which gives you x squared plus 6x plus 21. Then you can complete the square on that. And of course it will reveal the same thing, namely that x is minus 3 plus or minus 2i root 3. So it's kind of a question of taste on a given specific problem, whether you want to use the omega squared formulas or if you want to actually just divide out the linear factor and solve the resulting quadratic that's in there. Okay, at this point I thought, well, what is the cubic formula though, right? What's the analog of the quadratic formula? Why don't we just tell me it already? You know, what's all this u and y and z and omegas and come on, just give me the formula, man. Well, here it is. Here it is. If I have this cubic, all right, then I depress that thing to this. Well, we figured out that the q is this and the r is that. And we figured out the solution y plus z, where y cubed solves that, and r is that. And then from lemma 2, we know that u is 1/3 minus u minus 1/3 a is actually the solution to the big X problem, right? And so we have x is equal to u minus 1/3 a, where u is y plus z, which is y minus 1/3 q over y. But then, what is y? Well, y is the cube root of this, and y is the cube root of this. We get division by the cube root over here, still minus 1/3 a. And then, well, what is that? Well, minus r is all this, and big R is, what is big R? It's all this squared plus 4/27 q cubed, right? And then you got to subtract all of that times that, and oh, see, even so, I have still failed to make the formula explicitly in terms of ABC. See, I still, after all of this mess, I still failed to do what I wanted to do, which is, I still left this pesky q right here, right? Because q is what? Q is up here. Q is b minus 1/3 a squared. So I still, after all this mess, need to replace the q with that to have a genuine formula, just in terms of a, b, and c. But I'll leave it to you, okay? And I hope I have communicated to you with this page of my notes. Sorry if I was off the page. Here it is. So see, I technically should put that q in terms of, you know, these up there. This is the q, b minus 1/3 a squared. That should go there. And then I would have a stone cold formula with a, b, and c. This would be the analog of the quadratic formula for a cubic. So, yeah, I think you can understand why we don't teach this to high schoolers, right? And why you won't find this in, I don't think I'll find it in any algebra book that I have. I don't think I've seen this in the algebra books I've taught out of. I mean, maybe it's a special project at the end of a chapter or something, right? But as you can see, the cubic is just this much harder. Interestingly, the quartic is not, the fourth order problem is not similarly harder. It's about the same difficulty as the cubic, because when you look at if you depress the quartic, it ends up giving you there's something called, I think, the resolvent cubic. So you can take the quartic, turn it into a corresponding cubic problem, and then you can fall back on this stuff to solve that. Something like that. So the solution to the quartic is about a page long. Something like that. I mean, the solution to this one's about a page long. See, because even after all this, how do you find the other three solutions? Or the other two solutions, right? If you wanted an explicit formula in terms of coefficients, you'd have to couple this nonsense together with the, you know, the third roots of unity stuff. Yeah. And you got to understand, even after all of this cube root, what do I mean by it? This could be a complex number. What do you mean cube root of a complex number? Well, you need to know how to take the cube root of a complex number to make sense of these formulas, actually. Just saying. So this is both why we don't tend to teach this in high school, not this way anyway, and also why the formulas on page 6 are a better path, yeah, or page 4. All right. So here's another example. Here we have x cubed minus 7x plus 6, which, by the way, is nice. It factors actually as x minus 1, x minus 2 times x plus 3. So clearly the solutions are 1, 2, and minus 3. And let's see how the cubic formula makes it more complicated. So identify q as minus 7, r is 6, so the big R ends up being minus 400 over 27, which means we face y cubed is 1/2 of minus 6 plus the square root of minus 400 over 27. Again, check this out, right? This is a problem with real solutions, and yet the cubic formula necessitates the use of complex numbers. See that? Right there. Okay, so if I say x is equal to y plus z, I can use the cube root of that. All right. Plus 7 over 3 times the, you know, that's supposed to be cube root. My bad. These are all cube roots. Oh, wait a minute, is that the 3? I see what got me confused. There's a 3 in the denominator. There's also 3 in the root. The index of the root versus the 3 multiplied by 3 in this formula, yeah. Not the same 3. All right, anyway. 3's aside. You get this plus this, and the other two solutions, multiplication by omega and omega squared, and omega, they give you these, right? And I stuck these in the Wolfram Alpha just for my own personal curiosity, and this works out to 2. This works out to minus 3, and this works out to 1. Is that at all obvious? I don't think so, but, you know, there it is. So, actually, this would make, like, fairly, like, decent complex variable homework problems, you know, like prove this plus this is equal to 1. Whew. And not with a calculator, right, but with just direct manipulation. Well, I don't know, maybe with a calculator. Anyway, moving on. Point of this problem is just because we have a cubic formula doesn't mean we should use it, right? Another couple of examples. So there are special cases which are not covered by the cubic formula. For example, this is a very simple cubic, x cubed plus 27 equal to 0, and this is the case where if we look at the formula for z, we get division by 0 because the y is 0. So that's not going to work, right? So if we were doing this whole lecture more carefully, there probably needs to be a cubic formula for this case separate from the cubic formula in the case that y is equal to y is not 0. Because of course, if this is the case, then x is just equal to the third root of minus 27, which is easy enough to find, right? So we don't need basically this is kind of a choose your own adventure problem. If you've got only the constant coefficient in your depressed cubic, then we can just solve with a cube root directly. We don't need all this substitution nonsense. All right. Example 5. Here's one where we have the r equal to 0, but the q not 0, x cubed minus 3x. So my big R works out to minus 4. And so what do I get? I get big y cubed is equal to I. All right. Now I, remember, is e to the pi I over 2. All right. Because cosine pi over 2 plus I sine pi over 2 is equal to I. All right. If you forgot, remember e to the I theta is cosine theta plus I sine theta. And so that, in knowledge of trigonometry, allows me to go back and forth between the polar form of the complex number, right, and the Cartesian form of the complex number. All right. So I can convert an I to an e to the pi I over 2, and that's important because when I want to calculate the cube root of I, it's easiest to understand how to do that in terms of the polar form. Because in the polar form, I just divide by 3 the angle. So pi over I over 2 divided by 3 is pi I over 6. That's the cube root of I. And so that gives me also z. Once I've got my y, I get my z from minus q over 3y, which is, remember, q is minus 3, so minus 3 minus minus 3 over 3 is 1. 1 over y is e to the minus pi I over 6. So y plus z gives me that plus that, which is, by the way, 2 times the cosine of pi over 6, which is the square root of 3. And on the other hand, the other two solutions, like the omega squared one or the omega squared omega ones, they add together to give me root 3 or to give me 0. And so the three solutions here, of course, are that, right? Because that's not at all surprising, because, of course, this you could have factored, right? You could have factored this problem directly. You don't really need the cubic formulas to solve this problem, do you? Because, I think we all can agree that this we could do directly as x times x squared. Sorry, make sure I'm in. Oh, I'm x times x squared minus, I'm always not sure if I'm out of frame or not. I have to check here. X times x squared minus 3, which of course we could factor, times x minus root 3 times x plus root 3, right? So their solutions in terms of factoring, by the way, we got that. So of course the solutions are 0 and plus or minus root 3. But we can also derive them through the cubic formulas here. This is a relatively kind of moderate mid-level problem for the cubic formula. And then, finally, I thought I should at least have one example here where I actually depress the cubic and work through it, right? So here's that. So if I have x cubed minus 3x squared plus 6x minus 4, I substitute big X equal to little x plus minus 3 over 3, 3 over minus 3. And that, in this case, gives me x plus 1. Plugging in x plus 1, right, work that all out. So I could, of course, just go back and fall back on my general formulas for the depression here, but I decided to just do it directly. And so when you multiply these out, of course, the next deleting terms cancel, And what are we left with? We're left with x cubed plus 3x equal to 0. All right, which of course you could just solve using factoring, right? But I want to go through and illustrate the formulas again. So this is, I'm not solving this the smartest way. I'm solving this the way to illustrate the formulas in this lecture, okay? So we have q equals to 3, r equals to 0, and that makes the big R equal to 4. So y cubed is 1/2 this times minus r plus the square root of r, right? But the little r is 0, so it just leaves us 1/2 square root of 4, which is 2 over 2, which is 1. So y equals 1, and z is equal to minus 1. So my first solution, y plus z, is 0. And then I need to look at omega minus omega squared and omega squared minus omega, which end up giving me I root 3 and minus I root 3, which of course we could understand directly through factoring, you know, if you wanted to, much like I showed you on 9. But anyway, there they are. Now those are the little x's, right? Those are not the solutions to the original problem. These are the solutions to the corresponding depressed problem, right? And to get back the solutions to the original problem, put a smile on it, add 1. So turn that frown the other way. 0 plus 1 is 1. 1 plus I root 3, 1 minus I root 3. And these, my friends, are the solutions to x cubed minus 3x squared plus 6x minus 4 equal to 0, which means that you can factor this like this, which is also like that. So, yeah, there it is. This is a solution to the cubic. Now, the solution to the, solution to the quintic, all right, is a little bit harder, all right. In fact, so all of these things were found basically in the 1500s and certainly solidified by the early 1600s. And then mathematicians were chewing on how do you solve, so if we can solve the cubic, we can solve the quadratic since time immemorial. And then we solved the cubic, which was, thought to be unsolvable for quite some time. And but then people came to a solution of it in the 1500s, something like that. And then the quartics followed soon thereafter. So what about the next order, the fifth order, the quintic problem, right? So then in the 1800s, mathematicians, and I mean by 18th century, I mean not the 1800s, but the 17th century, 1700 to 1800, people tried to leverage these tricks I've showed you against the quintic problem, and nothing quite worked. And then people looked at all kinds of so you already seen, like in the cubic case, there's kind of a rotation of the roots that's going on, right? Like they're all based on that root of the roots of unity on the circle. There's kind of some kind of symmetry rotating between the roots. So that was some kind of idea like that there. And you can generalize this notion to what's called permutations of the roots. And I think Lagrange worked on this for decades and tried all kinds of different conceivable substitutions that you could think of, and just nothing quite stuck. And it became then the opinion of the mathematicians that it was probably not possible to find a general formula for the quintic. And then in the early 19th century, about 1812 or so, there was what's largely considered to be flawed proof by a fellow named Ruffini. And I don't think people who try to understand the proof now are people who, I haven't seen anybody speak positively of that proof, algebraists that I know. But then Abel, in about 1820 or so, gave a proof that no, it was not possible to find a general formula in terms of radicals, like I gave you in this lecture for the cubic, for the quintic, okay? And then in 1830 or so, a fellow by the name of Galois, came up with what's called Galois theory. And so it's like here's chapter 32 in Galilean's abstract algebra. And if you leaf through here, you know, this is the end of junior, senior level course in, abstract algebra. And you could leaf through here and he'll basically give you a strategy for deciding when it is possible or not possible to solve a quintic problem by radicals. And, it's possible to teach to undergraduates, math majors. This is a Contemporary Abstract Algebra 4th edition. But to do Galois theory properly, it's probably like a semester course. I teach it improperly in about a third of a semester in Abstract Algebra 2. If you want to see details, you can go look at my course. But, it turns out, though, that for the 5th order problem, you can calculate something called the Galois group. If the Galois group is what's called a solvable group, that means that there's a way to solve the corresponding quintic equation in terms of formulas involving radicals. All right. But on the other hand, if the Galois group is not solvable, for example, it could be what's called a simple group is not solvable, then it is not possible to find the solutions to that quintic in terms of formulas involving radicals. In other words, there is no analog of the quadratic equation for such problems. So that's a very, very interesting turn of events, that you can work out n equals 1, 2, 3, and 4, and then all of a sudden at n equals 5, you can't do it anymore, in general at least. But on the other side of things, it was actually the birth of modern group theory, the study of this problem. So studying solutions to polynomial equations is one of the entryway points to what's known as group theory, or more largely the study of abstract algebra. The other point of entry for group theory is in transformation groups, understanding what kind of transformations leave a shape unchanged. How can I move this thing around and still have the shape that's there? Anyway, symmetries and transformations is the other entryway to group theory. I think that's it for this one. So thanks, guys.